morning, everyone. In this week, and especially in this lesson, we will talk about the text detection for a given image. Okay, and so 3 text OCV text detection is given in here. Okay, so we need to firstly give the x1 text detection with easy OCR. Okay, easy OCR is a library that's built in the Python programming language, and so we can install easily using the pip install easy OCR code in the terminal like this one. Okay, and so it's used to analyze the image to extract the information containing with the text. For example, I am Mehmet İşcan for a given text, and so this easy OCR analyze this image and take the pixels or the grayscale format of this image, and then hit apply to some convolutional filters or the neural network applications to this image, and then easy OCR obtains to the text from this image, and then this gives us the exact string representation in the Python programming language. Okay, so we should use the CV2 library, and also we should import the easy OCR. Okay, if you don't have any easy OCR library, you can install this library using the pip command. Okay, so we should define the reader in the first place. Easy OCR reader is an function, and we should give the type of the containing text in here. For example, if we have the Turkish words for a given image, and then we should give the tr, but in this text we have the English words. Okay, and also if you use the GPU in here, because it utilizes the PyTorch library for analyzing the image to extract the information related to the text. Okay, and so if you don't have any CPU, you can assign this true value as a false. After that, we should give the image path in here text1 png in this case, because we have this kind of image. It was the best of times, it was the worst of times, it was the age of wisdom, it was the age of foolishness. Okay, and so this is the R key or the text, but within the image format. Okay, and so this tool gets this image in terms of the matrix presentation or NumPy matrix. Okay, and so we need to inbreed this image path and then we have this image like this one. In the terminal, we have the matrix representation of this image, because we have the RGB code in here like this one, and so this matrix represents to our generation of this image. For example, 255 represents to the white code in here, but in the text format we have the black lines, for example 0, 0 and 0 for the RGB codes. Okay, and then we can analyze this matrix, NumPy matrix, in order to get the text or strings from from this image. But how can we do that? We should define the results in here, the reader read text, the automatic function or the method for this image, and then if we put the image into the read text, and then this read text returns to to our probability or the text or the box location of this text for a given image. Okay, and so if this is the case, we can use the detected text in here, like this one, for B box text and probability in results. Okay, and we can print the whole the text like this one, text and text. Okay, so if I rerun this code, and then we will have the some string character contained in the what, in the text. Okay, and so at each line or each boxes we have the detected text. For example, text, it was the best like this one, this is the first line, and times it was the worst, times it was the worst, and of times it was the age of wisdom, it was the age of foolishness. Okay, and so this tool creates the patterns in here, or split this image into 1, 2, 3, 4, 5 area, or the box, and then take this image in here and it feed this pattern into the what, into the R neural network, or the deep learning applications, which is in this case we have the PyTorch library in here for train to the what, to the getting the information from the image to what, to provide the text. Okay, and then this function returns to the what, the specific text and probability of our application. Okay, so this is the easy example for our text detection application, and that's enough for this lesson because this is the Python programming language, but you can easily implement this algorithm in the what, in your application. So the main topic of this lesson is the curve fitting method, in especially for the mechatronic applications, or the what, or Python programming language. Okay, so we have the head title in here, curve fitting in Python. Like this one. So what is the curve fitting? For a given any data coming from measurements. For example, in your mechatronic system we have the encoder, or the analog sensor, or the what, the voltage level sensor, and then we take the measurements by using what, the serial port or the CAN bus application, and then this codes is converted into the what, into digital codes or the matrices. Okay, and then these measurements or the data generation can be fitted into the what, one specific model. For example, if we have x 1, 2, 3, 4, 5, 6 and blah blah blah, and y 1.1, 41, 444, 1, 2, 3, 3, 3 and blah blah blah. Okay, and so these are the measurements or measurement matrix in given here, vector in given here, and this is the input matrix. Okay, and then we can easily set the what, the some specific sensors to the what, to the model, to analyze it. Okay, in the next lessons for the what, the sensor and its application, or the control theory or the system dynamics, we need to fit the what, the sensor calibration into the what, the some measurements, in order to provide the correct estimation or correct measurements for your application. And so in this case we need to build some mathematical model to correct it, or to model this representation by using the what, by using the, for example, 2 coefficients or the 1 coefficients for a given input data, or the x. Okay, And so we can define a new model with a specific coefficients in order to what? Fit the whole data. Okay, in Python we have some tools, for example CGPy, okay, curve fitting with CGPy optimize. This optimize function is also used to what? The optimal programming or linear programming application, which means that if we have any matrix or the data, and so we can fit the many coefficients using this optimization tool in order to minimize to the least square error, okay, or infit. This is another library for the curve fitting and parameter estimation for nonlinear least square application, okay, or optimization. Maybe you don't know anything about the optimization or the estimation, but in the next sessions or the next another lessons you may utilize this, okay. Or we can use the scikit learn library for the regression operation. What's the meaning of the regression? Regression means that we can build the model for a what? For a given x data to the y, okay. This is called the regression, or non-linear regression can be applied in here. And we can also utilize the SymPy, symbolic toolbox, to optimize and model curves for a given data, okay. We can build some equation for with the symbolic representation, and then we can apply some mathematical rules. In MATLAB we have also a similar toolbox, and this is the same idea for a given the Python programming language, okay. So in the first example we should create the linear model fitting, okay. Firstly, in order to do that, we need to import the NumPy as MP. We need to visualize the whole data by using the pyplot as PLT, and from CGPy optimize import curve fit function, okay. So firstly we need to create some data, generate some example data in here. X data can be created the MP linspace 0 to 5 and 100 data is given in here, okay. And so we should create the true params for it. For example, sin, for example 2.5, 1.2, 0.5 and 0.2. This is the offset parameter, and we can build the generate the R sessions. Sine model is created with the X data and start true param sin, okay. So we can fit the multiple variable or these terms by using the star operation, but we need to build the sinus model in here, okay. And sin model can be created with the x, a, frac, phi and offset, okay. And so return to the a times mp sin 2 times pi mp pi times frac times x plus phi plus offset values, okay. This true params contains the a, frac, phi and offset in here. So for this case we can plot the plot scatter data, x data, y data, and label must be assigned to the data, okay. But we can show this parameter in here, for example plt show can be built in here like this one. And so we have the some measurements in here. For example, this is the sinus data, and so this sinus data contains the what, the up to 2.50 and minus 2.5, and so we have the frequency values of the what, the 1.2. okay, but we can also do another fitting techniques in here. For example, if we have this data in here, we can build the params linear with terms of the what, the curve fitting function. This curve fitting function takes the linear model, okay, and we should provide the x data, input data, and y data, okay, and so we need to define the what, the linear model also in here like this one. Def linear model x m c and returns to the what, the m times x plus c, okay. These are the linear model because we have the one-dimensional data x and we have also the c values in here, okay. So if we put this function, this linear model, into the curve fitting with the what, the input and y data, and params linear returns to the what, the correct values of the linear operation. For example, if the r curve fitting is okay in here, is optimized the r parameter, and then we can define the y fit linear function. The linear model can be given with what, the x data, because it's the input data in here, x, and m and c are params. For example, params linear, okay. And we should plot to the what, plot x data, y fit linear data, and we should give the r, and label must be equal to the what, the linear model, okay. So this is the real data but this is the what, the r linear fitting data, and PLT show must be shown in here like this one, okay. This params linear curve fitting linear model x data, okay, and params linear this is the one expected, okay, x data, params linear x data, y fit linear, and we should also call this one, okay, curve fitting. I'm sorry, we should give the what, the anonymous character in here, okay. So in the linear expectation we have the what, this sinus signal in here, but we cannot model it because this sin signal cannot be modeled by using the first order dynamics or the linear models, because in the linear model we have the bias value and the one coefficient related to the first order of the x values or the input data, okay. And so how can we create another formulation? This is not okay for us because the linear model cannot be modeled by using this curve fit method for for a relation between the x data and the y data. And so we should different proposing the model, quadratic model to the data. What's the meaning of the quadratic? Quadratic means it's the squared form of the r params, and so params quadratic should be defined in here like this one, the curve fit, and quadratic model should be defined as a function in here, and x data and y data should be given here. And so this quadratic model can be defined with def quadratic model in here like this one, and so we should provide the x, a, b, and c. For example, a times x square in here, return a times x over 2 plus b times x plus c. Okay, these are the proposition for the what? For this sinus model. Okay, so if we have these terms, and then we should create the what? The y fit quadratic in here, like this one. The quadratic model should be built with what? The x data. These are the input data and params quadratic. Okay, after that we should plot the what? X data, y fit quadratic, and after that we should assign the g green, and label is equal to the what? The quadratic model. Okay, so if I rerun this code and then the R model should not contain the R representation, because the sinus is more complex signal to build these factors. Okay, so how can we correct these terms? And so if we know that this is the representation of what? The sinusoidal signal, we should propose the what? The proper formulation, and we should fit the sin model to the data. For example, the param sin, and we should give the arbitrary number in here, and curve fit should be provided with the what? The sin model and x data and y data. Okay, and we should fit the y fit sin model x data with the what? The params sin. Okay, and we should plot the what? The R parameters in here, x data, y fit sin data this is the blue line, and label sin model. Okay, this is the R last form for curve fitting operation. Okay, and so we need to plt show the legends. Plt x label is equal to the what? The x, and y is equal to the y, and plt title must be given in here, curve fitting examples with different model. Okay, and after that if we run this code, and this sin model fits the whole the data in here. Okay, but how is the correction rate or the performance gradient in here? We should print the what? The param sin or linear model parameters can be given with the what? The params linear. Okay, and the quadratic form should also be given in here. Quadratic, and also we should give the what? The sin model parameters, param sin. Okay, and so if I rerun this code, and then I have this figure, but in the sin parameter model, in the first place we assign to the what? To this model 2.5 1.2 in here, and the sin parameter in the third place we have the 5 minus 5.17, and so this is wrong. But our model is okay with you in here, because in the curve fitting or the optimization algorithm we cannot reach the exact solution of the R system, but we can only approach to the what? To the similar values. Okay, not we have the corrected estimation in here, 3 of the 4, and then 1 is not enough in here, but this is the 5 values. Okay, but in this case we have the high performance in here. Okay, but we have the similar or some slight error values happens in here. Okay, so this is the first example about the curve fitting application. You will always use this curve fitting technique in your applications, because the in mechatronic engineering, we always use the sensor or the actuator for the what? For modeling the any sensors or the actuators. Okay, so this techniques is important for us. And linear curve fitting can be created in here. Okay, firstly, another application is given in here. Import matplotlib pyplot as plt, and from cgpy optimize is our function. Import curve fit. Curve fit is the specific function to be utilized in these applications. Okay, and so in this case we will try to define linear model, def linear model xy a b and x1 and x2 xy, and the return values of the a times x1 plus b times x2. Okay, and so in this case we have the two inputs with a linear form. For example, one input is the x1 and one input to x2, but we need to find the exact values of the a and b in here. Okay, and so in order to do that we need to generate the synthetic data. Data, but in your real application you always have this data. For example, the x1 is the temperature measurement coming from the sensor, and the x2 is, for example, the pressure values from taking the pressure transducer. Okay, but in our application we need to generate these values because we don't have any sensor in here. We should assign the random C in here for reproducibility. X1 data mp linspace 0 5 to 100, and x2 data is assigned to up to 3, for example, and x1 data x2 data can be mesh grid in here like this one, x1 data x2 data. Okay, and for example the true params or the true values of the a and b, in this case for example 2.5 1.2, and so after the every operation that's built in the optimization tool, we don't know the a and b, but if we are using the curve fit coming from the CGPy optimize, and then we will reach this data. These are the true data. Okay, but in your application, in your mechatronic application, you have the sensors on the pressure transducer and you don't know anything about these true parameters. But in this case we generate this synthetic data, but the algorithm does not know these true params. And so how can we generate the y data in here? The output data, linear model x1 data x2 data is given in here, and true params must be given to the linear model. Okay, after that this creates we should flatten the whole the values in here, the data and the output, and x1 flat x1 data dot flatten means that we convert everything into the one-dimensional vector. Okay, and x2 data, and also we should give the y flat y data flatten. Okay, so firstly we have the for this linear application. Firstly we should give the initial gas. These are the initial gas for the 2.0 and 1.0 for the a and b, but the real numbers is the 2.5, the other numbers 1.2. but for example I choose the first values 0.5, and this term is the 1. Okay, and this one must goes to the 2.5, and this 0.5 goes to the 1.2. This is the initial condition of our optimization algorithms. Okay. After that, we should generate the params and covariance in here, because we have the two-dimensional data in here. And so can use the curve fit in here, like this one, the linear model, and x1 flat should be provided in here, x2 flat should provide in here, and y flat is the target data in here, and the p0 is equal to the what, the initial gas. Okay, so a fit and b fit is calculated in this params. Okay, so we can print also the what, the a estimated like a fit, and we have the b estimated values with the what, the b fit. Okay, and so if I run this code, and then we have the 2.5 and b estimate 1.2. It's correct, but if I choose the 150 100.5, and so this estimated values is also now is correct. In the linear optimization or the linear programming, and then we can find the whole the values in maths to the what, to the correct values of the a and b, but in nonlinear formation we cannot easily do that. Okay, just remember that. So it's the case, and so y fit is assigned or build these values, x1 data, x2 data in here, and a fit and b fit must be provided in this code. And also we generated what, the mean squared error values. This is the specific index MSE for the what, for the error between the R fitting data and the real data. This general expression for the what, for the machine learning application, statistic, probabilistic theory, and you will always see this code, MSE, mean squared error. Just remember that. Okay, and so MSE can be calculated with what, the MP mean values, with the what, with the real data, y data, and y fit, and we should also generate what, the square form of these terms. And so if taking the mean values of these terms, and so this is the equals to the what, the mean squared error form. Okay, so how can we draw these terms? Draw subplots in here like this one. Firstly, we should give the fig and axis in here like this one, PLT subplot with the dimension of the 1 row and 3 column in here, and we should give also fig size values in here like this one, 18 and 60. And firstly we should draw to the what, the true data. Okay, in 1 is equal to the axis 0, which means that this is the first plot, and so im show can be given in the what, the y data, and extend the specific utilization of this im show values in here like this one, 0, 5, 0 and 3. These are the maximum values and the minimum values for a given dataset. Okay, and origin must be setting into the what, the lower, and CMAP is the what, the where it is. Okay, axis 0 set title can be assigned with the what, the true 2D data, x1, x2. Okay, and y label is the what, x1, no, x2, and x label is the x1. Okay, so the same idea is current for the what, the axis 1. Okay, but in this case we should fit the what, the y fit data, and lower fit this. Okay, and so this is the fitted data. Okay, and also we should provide the what, the R error values or the residual values in here. issue and y data, y fit. Okay, these are the what are difference between the real data and are the fitted one. Okay, and so but in this case we should provide the what to, and residual is given in here like this one. And so residuals y real, y model. Okay, so also we need to create the color bars in order to what to represent the which part or which section of our true data and y-fit data cannot match or the couldn't match in the what in the space of the y data. Okay, for example x1 and x2 between the what 0 to 1 or 0 to 2, and then we can say that this color bus represents to the what highest error value or in the form of the red. But if we have the smaller number of the errors or the residuals in here, and then this is indicated with the what with the blue lines. Okay, and so c bar 1 fig color bar can be assigned in here in 1 axis 0 and label is equal to the y, orientation is the vertical. Same idea is given in here in 2. Okay, but the axis 1 in 2 and in 3. Okay, so the last case PLT subtitle can be assigned with the what the f mean squared error MSE can be assigned with the what with these terms MSE values. Okay, and the font size is equalized to the what to 16. Okay, and PLT tight layout should be assigned and PLT show must be given. Okay, and so if I run this code and then we have the true data representation. For example, this is the what the highest values of the R representation in the Y data, but this is the what the lowest values of the Y data. Okay, in 3D generation we can add the some another dimension in here in order to represent the what the Y axis, but this is some beautiful form for to what the showing your data representations. Okay, for example at the 5 and the 3 values, and then we have 5 and 3 the 500ths value at the Y data. In the fit data just like that, that's the dissimilar, but we have the some denotations in here like this one. Okay, and these residual values proposed to the what to our error signal in here. Okay, and also we can add the what to some another color bar in here. For example 3, 2 and 3 can be given in here like this one. And so these are the what the lowest values of the what the 1e minus 14, which means that we have the smallest values of the error. But in this case we have in the blue line in here we have some error increased in here, but it's negligible. Okay, these are the generation or the total representation of the what the R implementations. Okay, so any question? Okay, if there is no question, and then we need some break in here, and after that we will continue with the what the non-linear fitting application. Okay.